So in this video, we are going to talk about acyl chlorides. Acyl chlorides are basically the derivatives of carboxylic acids, which are formed when carboxylic acids react with any of the following compounds. And the following compounds, these are the three compounds, and they are very important. You need to learn them. Okay, first is PCl3 plus heat. Heat is required when reacting carboxylic acid with PCl3 to form an acyl chloride. This condition is important, and this is the only reagent that requires heat. Then the second reagent is SOCl2. Uh, PCl3 is a colorless fuming liquid. Okay, this is its physical state at room temperature. SOCl2, which is also known as thionyl chloride, it also reacts with carboxylic acids to form acyl chlorides. And SOCl2, the thionyl chloride, also does not require heat. PCl5 is a white solid at room temperature. It can also react with carboxylic acids to produce acyl chloride as the major product. Okay, and it also doesn't require heating. Okay, the general formula of carboxylic acids is RC double, oh sorry, of acyl chlorides is RC double bond O and Cl. It's just the OH group from the carboxylic acid has been replaced with a Cl with a chlorine atom over here. This is the general formula, and I have also written the equations of each of the above given reagents, and they are asked in the exams. These equations are important. I learned the three equations, and the major product is important, and the reactants, the reagents which are used as the reactants are important. Okay, now let's look at the first equation. Our carboxylic acid over here, RC double bond OOH, reacting with PCl3 in presence of heat, produces an acyl chloride. The OH group over here, it gets replaced by a chlorine atom right over here, and given phosphorus acid as the byproduct H3PO3. Okay, then the second equation. Oh guys, these equations are asked in the past papers, so please do learn them. Then the second equation over here is the reaction of carboxylic acid with PCl5. We get again the acyl chloride. The number of carbon atoms are the same in the carboxylic acid and the acyl chloride. Okay, just the OH group is being replaced with the Cl. Okay, the POCl3 trichlorophosphorus 5 oxide. Trichlorophosphorus 5 oxide is given as the byproduct, and HCl is also given as a byproduct. Okay, then the third reaction is reaction of the carboxylic acid with SOCl2 thionyl chloride. This gives off acyl chlorides, sulfur dioxide gas, and HCl, fumes of HCl also in the gaseous form. Since both the byproducts are in the gaseous form, they'll escape, and we'll get our acyl chloride as the only product in the third reaction. So therefore this reaction is considered the best for preparation of acyl chlorides. So SOCl2, and by the way, SO2 over here is a pungent gas, and it has a pungent odor, a choking smell, pungent choking smell. It is acidic gas. It has a pungent odor. Acidic gas and a pungent odor, and HCl is also produced in gaseous form. Okay, now let's look at the physical properties of the acyl chlorides. Okay, so I've listed them down. Let's read them. They are usually liquids at room temperature. They fume in moist air. They basically produce fumes when they are exposed to moist air. They are immiscible with water, but eventually react with water and dissolve in it. So basically, initially they are immiscible. They do not mix with water in liquid form, but they do react with water and they dissolve in water. Okay, and then the fourth property, a very important property, is that The main intermolecular forces. The main intermolecular force is the permanent dipole interaction, which is present due to the presence of the permanent dipoles in this. Uh, the dipoles present in the acyl chlorides, basically the carbon double bonded oxygen dipole and the carbon chlorine dipole. They are responsible for the permanent dipole interactions. Basically, the carbon double bonded oxygen is the major dipole responsible for the permanent dipole interaction in acyl chlorides. When permanent dipole carbon double bonded oxygen, the carbonyl group, is also present in ketones, R, C double bond O R. So in that case, also permanent dipole interactions are present, and this bond is also present in aldehydes. So in aldehydes as well, the permanent dipole interactions are present due to the dipole. Okay, now let's compare acyl chlorides with alkyl halide. This is a very important part and has been tested frequently in the exams. So let's get started with it. A comparison of acyl chlorides with alkyl halides. Basically, acyl chlorides are more reactive than alkyl halides. Now let's talk about it why. Basically, if we look at the acyl chlorides, there the carbon is double bonded to an oxygen atom, and at the same time, which is electronegative. Oxygen is highly electronegative, and at the same time, the same carbon atom is bonded to a chlorine atom, which is also electronegative. So these two electronegative atoms, they basically pull a lot of electron, they pull the electron density away from this carbon atom. So as a result, what happens is that the magnitude of this partial positive charge, it increases. So basically this carbon over here is more electron deficient compared to the carbon in alkyl halides, because the carbon in alkyl halides is connected only to the chlorine atom, which is electronegative. But oxygen and chlorine are both bonded to the same carbon atom in acyl chlorides. So since this partial positive charge on the carbon atom is a lot more as compared to the partial positive charge on alkyl halides, so the alkyl halides are more reactive towards incoming nucleophiles. Nucleophile is any species which is attracted to region of positive charges. So if the nucleophiles are attracted to regions of positive or partial positive charges, partial positive charge over here in acyl chlorides is a lot more as compared to the alkyl halide. So the nucleophile is more likely to attack the acyl chloride, and hence it is more likely to react with the acyl chloride. So therefore, acyl chlorides are more reactive towards nucleophiles because there are two electronegative atoms attached to the carbon atom, and the magnitude of the partial positive charge is much more in acyl chlorides compared to alkyl halides. Now, I've also put this in words, and this is an important part and is usually asked for 2 to 3 marks. Okay, now the carbon atom in acyl chloride is attached to two electronegative electron withdrawing atom. Electronegative or electron withdrawing, they are basically electron withdrawing because they pull the electron density away from the carbon atom, leaving a partial positive charge on the carbon atom. The oxygen and the chlorine, they pull the electron density away from the carbon atom, making the partial positive charge on the carbon atom greater than that which is present in alkyl halides. So basically, I've talked about it that the partial positive charge in acyl chlorides is more than the partial positive charge in alkyl halides, and so the carbon in acyl chloride is more electron deficient. This is a keyword. It's better to use it, and hence is more reactive towards incoming nucleophiles. So this is the reason why acyl chlorides are more reactive towards incoming nucleophiles, because in the carbon atom in acyl chlorides is directly bonded to two electronegative atoms, whereas the carbon atom in alkyl halides is bonded to just one electronegative atom, which is the chlorine atom. Okay guys, so thank you so much. Now meet you in the next video on the reactions of acyl chlorides.